Okay, hello everybody. This is the second video clip for the lecture on spatial autocorrelation. Last time, we stopped here on this slide. Basically, this slide shows you how to use a specific method to calculate uppercase L, which is what? Which is the total number of joins in a specific example. And this example here is a chessboard, right? With black and white cells. And we use BB, WW, and BW. Their O value, O represents observed, to address the number of joins, of different types of joins, BB joins, WW joins, and BW joins. So more example using this method is shown here. Okay, so in case 1, case 2, and case 3, there are different numbers of BB, BW, and BW. Case 1, I introduced this before, right? So 0 BB joins are 0 WW joins, but 24 BW joins, right? And because the total number of cells stays the same in these 3 cases, so total number of joins stays the same, okay? But in case 2, there are 5 BB joins, 7 WW joins, and 12 BW joins. In the third case, right, 10 BB joins, 10 WW joins, and 4 BW joins, right? But the total number stays the same, So next, how to test it? Join count statistics test. So requirements, each cell is assigned either black or white. So the value for each cell here must be binary, okay? Of course, black and white, this configuration is very convenient. Of course, you can change it to 0 and 1, green and blue, or whatever you want, as long as it is a binary system. And each pair of cells are defined as adjacent or non-adjacent in a consistent manner, which means you have to apply the same definition of neighborhood on this whole chessboard. Okay, you cannot change the definition of neighborhood during your calculation. So as usual, our old friends, hypothesis, right? So the null hypothesis here is that the number of BW joins is equal to, the observed number of BW joins is equal to what? The expected number of BW joins. If that is the case, we say the area pattern is random. There is no spatial autocorrelation. Okay, that's null hypothesis. And if they're not equal to each other, we say there is not random or there is spatial autocorrelation. That's a two-sided test, right? Of course, the observed number, if the observed number is larger than expected number, which means there are a lot of BW joins, then there are more BW joins than expected, then we say this pattern is more dispersed than random. Okay, different cells, they're dispersed at different positions on this board. On the other hand, if the observed BW joins number is smaller than expected value, then we say the area pattern is more clustered than random, which means that there is less BW joins than expected, which means there are a lot of BB joins and WW joins. What does it mean? It means that similar cells, they are clustering. Similar cells, they are clustering, okay? It means that the spatial pattern here is more clustered than random, okay? So yeah, we're going to use z-test. Under null hypothesis, join count statistic has a normal distribution, and we use z-test directly. We don't have to talk about standard deviation or the number of of your observations anymore. Simply use z-test. So we have three z-statistics, ZBB, ZBW, and ZBB, ZWW, and ZBW. So their definitions are similar to each other, right? Let's just use ZBW for example. So we have numerator and denominator. The numerator is the difference between observed number of for this specific case, BW, ZBW. It's the difference between the observed number of BW joins and the expected number of BW joins. And denominator is the standard deviation of BW joins. Okay, we calculate this ratio, and since this test is about the comparison between observed BW and expected BW, so the most important formula among the three is the last one, ZBW. Okay, now let's talk about the standard deviation of BW. Before that, we need to define more parameters. Let's just suppose we have NB black cells and NW white cells. If totally we have N cells, the difference between N and NB is NW, right? Because there is either black cell or white cell. Okay, so under the null hypothesis, the probability of a cell being black or white is what? Is PB or PW. PB is the ratio between NB and N. Makes sense, right? There are totally N cells. NB of them are what? Are black. So the ratio is a probability of finding a black cell if you just randomly choose a cell, right? So similarly for PW, PW is the ratio between NW and the total number of cells, N, right? So the probability of finding BB is the squared PB, which means I will randomly choose two cells. They must both be they must both be black to have this, right? To have this BB joins. If these two cells, they are neighbors, right? So similarly for WW, the probability of finding a WW join is the square of PW. So if we have a join of BW, and the probability of finding that is 2 times of PB multiply PW, because it could be a white cell and black cell or black cell and white cell. So we'll add them up. The total probability is 2 times of the product of PB and PW. Okay. After this definition, we define more. So here, the expected number of BB join is actually equal to the average value of number of BB joins. So totally we have L joins, and the probability of finding a BB join is the squared PB. So this is the expected value for the number of BB. Similarly, we have the expected value for the number of WW. And let's just go on. We have the expected number of BW, which is equal to 2 times of PB multiply PW multiply the total number of joins, uppercase L. So we have expected values for BB joins, WW joins, and BW joins. So here comes the important part. The standard deviation of BB, WW, and BW is different from we use is different from the definition of standard deviation we have been used this semester. So here you just need to remember the standard deviation of BW. It's a function of what? Of PB, PW, and K and L. So everything here has been introduced except K. So K is a constant here. K is the constant here. Okay, so it's a little bit different from L, but it's still about what? The sum of Li. The sum of Li. Li is what? Is a number of neighbors for a specific cell, right? So we use this specific summation to define another, say, constant K. Okay, so if we can calculate K, we can calculate L, and we know the value of PB and PW. Eventually, we can calculate the standard deviation of BW. Okay, I'll show examples here. For example, we have this chessboard, and black cells and white cells. It's a binary chessboard, right? We want to calculate different parameters to eventually decide if there is spatial autocorrelation or not, right? And this is the purpose of joint count method, right? So firstly, null hypothesis and alternative hypothesis. Of course, the null hypothesis is that the observed number of BW is equal to the observed number of expected number of BW. Observed, expected. If they are the same, then we say there is no spatial autocorrelation, or in other words, this area pattern is random. If that is not the case, they are not equal to each other, then we say there is spatial autocorrelation or area pattern is not random. Okay, so I will show you this huge table. So the first column is the number, is the name for each cell. We have cell 1, cell 2, cell 3, cell 4, go on and go on and go on. Eventually, this cell is cell 16. We have 16 cells. And the color for cells, right? And the number of BB neighbors, the number of BB joins for each cell. For example, for cell 1, there are 2 BB joins for this specific cell. Of course, here we are using Rook's case, right? So there are 2 joins for this specific cell, cell 1. Join 1, join 2. They're both BB cell joins, right? So there is no WW joins for the first cell. It makes sense, right? And of course, there is no BW joins for the first cell. So the total number of cell, or the total number of joins for the first cell is 2. Join 1, join 2. Both of them are BB, right? So we also need to calculate K, and K, in order to calculate K, we need to know the product of L and L minus 1. So 2 multiply 2 minus 1 is 2. Okay, so this is content of this table. We do this for each cell. It's again, it's a time-consuming work, but eventually you have this table, and total is simply the total for each column, right? So totally there are 10 BB joins, 14 WW joins, 24 BW joins. That's also the total number of joins on this chessboard, right? The sum of L is 48. Oh, sorry, this is BW. This is the 24 is the total number of BW joins. L is the total number of what? L is representing the number of joins for each cell. You add them up, there are 48 joins. And the sum of L multiply L minus 1 eventually is 104. So let's see what's going on here. In this small table, MB is the number of black cells, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. On the other hand, 8 white cells, and the probability of finding a B, of finding a black cell, is 0.5, because totally there are 16 cells, 8 of them are black, 8 of them are white. So half, 0.5 for finding a black cell, 0.5 for finding a white cell. And the uppercase L and K, you can go back, review those two formulas for L and K. They are based on the table here. You can use this table to calculate K and L, right? And what else? Standard deviation for BB join, for WW join, and also for BW join. And expected number for BB, WW, and BW. I have introduced the formulas before in the last slide. Sorry, 2 slides ago, and you can go find them. And eventually, ZBB, ZWW, and ZBW, the three Z statistics, they can be calculated. So most importantly, we care about ZBW because null hypothesis and alternative hypothesis, they're both based on what? BW. We want to use ZBW to test if OBW is equal to EBW or not. Okay, so we have a Z value for BW joins, and its value is 0. So I don't even need to go to the lookup table, right? Because 0 is just in the center of the normal distribution, standard normal distribution, which means that it's not possible to be in the reject area. It's in the center, right? So we have to accept the null hypothesis that OBW is equal to EBW, which means that the area pattern is random, which means there is no spatial autocorrelation on this chessboard. So that's the result. So you can say you have to make this table, right? List all those parameters you need, right? Here, and standard deviations. And also you need to calculate the expected value for them. But I mean, if you're facing a question asking you to do the test, you can simply calculate ZBW and ignore ZBB and ZWW, because eventually we're trying to find out the relationship between the observed BW and the expected BW instead of BB or WW, right? So here, like I said, we only care about the Z value for BW joins, and it is 0. The absolute value is also 0. It's just too small, right? It's in the center of the standard normal distribution. So it's pretty safe to accept the null hypothesis that there is no spatial autocorrelation here. And the application could be what? Could be this. Did the blue and red map really say something significant about the locations where people voted by county in 2000 presidential election? So this is a US map by counties, yeah, voting by county. And blue counties, they are for Gore. Red counties, they are for Bush. Let's just take a glance here. Do you think there is spatial autocorrelation here? I would say yes, because you can say that most, I would not say most, let's just say this more accurately. We can say that blue counties, they are clustered at different parts of the country here, right? On the West Coast and on the East Coast and some areas in Midwest. But at a glance, we can say that, we can tell that there should be spatial autocorrelation, right? If we consider red as a background, and on this background, blue counties, they are clustering. So this is just our conclusion based on a glance, and we want to quantify that. The method is the same. So we used black and white for chessboards. So this is not a chessboard. This is United States, but it's the same. Each county can be considered as a cell, but here we use another pair of colors. Instead of white and black, we use what? Blue and red. So yeah, I'm not going to introduce these parameters one by one because they're very clear. And all those parameters we use, like a probability of Bush winning at a county, which is the probability of finding a what? Of finding a red cell is here. And the probability of finding a blue cell is here. We also can calculate L and K. You can see the results here are pretty big because there are so many counties in this country. But eventually, the background, the things we want to calculate here is the same, right? Number of BB joins, WW joins, BW joins, and the expected values of them. So eventually, we want to calculate the standard deviation for BB, BW, BB, WW, and BW, right? And then after that, Z value. So again, let's focus on ZBW. ZBW the absolute value here is pretty big. It's 17.385. So for this specific example, I would say no matter you are using what type of, what value for alpha, this absolute value will be larger than, I would say, any value in that lookup table for z-test, right? Which means that this specific value is safely in the what? In the rejection area, which means that your z statistic will be larger than your what? Its absolute value will be larger than your critical value. Absolute value of critical value, because it's negative here, right? So what does it mean? It means that we need to reject the null hypothesis, which means there should be or there is, because the null hypothesis is that there is no spatial autocorrelation. And due to this huge z value, we need to reject that. In other words, there is spatial autocorrelation. And this conclusion, this conclusion based on the quantified parameters is consistent with the glance we had, right? Remember that when you're looking at this map for the first time, and you can tell that the blue areas, they are clustered within different parts of this country. That's your impression. Yeah, your impression is correct. Eventually, according to statistics, there is spatial autocorrelation. All those blue areas, blue counties, they are clustered. They're clustered in different areas of the country. So it's very useful for the finding or for the judgment of spatial autocorrelation. If your study area is divided into small cells or small units, and it's a binary situation. If it is not binary, you cannot use this join count method. Okay, so next we're going to talk about Moran's I, and I'm going to stop here and see you in the next video clip for this lecture. Thank you.